Hello everyone. In our last video, I may have blown up your brain. I'm hoping I did. But this gravity isn't real stuff, and so I want to follow up a little bit about it. I'm not reneging on it by any means, but just going to try and help you feel a bit better about it. So, quick review of some of the things. If you can feel a force contacting you, in other words, you feel a force pushing you sideways, accelerating you. Do you feel like you're accelerating? Yes, you do, of course, right? If you can't feel a force contacting you, then do you feel like you're accelerating? No, right? F equals ma. If you're standing on the ground, do you feel a force contacting you? Yes, you feel the floor on your feet upwards. So do you feel like you're accelerating? Yes, you do. But, do you naturally think you feel like you're accelerating? No. Okay, because your brain sees that you're not accelerating relative to Earth, and so it kind of tricks you into thinking, oh, this is just what not accelerating, or sorry, yeah, not accelerating feels like when you're on Earth, right? In the presence of the gravitational field of the big mass that we're stuck to, right? If you are freely falling, no air resistance at all, right? Do you feel the force contacting you? The answer is no, you don't. You don't feel gravity pulling on your feet or pushing on your head. You just don't. Do you feel like you're accelerating then? Well, the answer is actually no, right? But of course, your brain tricks you into thinking that you do feel like you're accelerating because clearly you're accelerating towards the Earth. Okay, so if you're falling at terminal velocity, do you feel a force contacting you? The answer is yes, because in terminal velocity, your free body diagram would look like this. You'd have this applied force of air resistance up, right? And that would be against gravity force. And I know you're probably thinking, well, like, how can we draw that gravity force on there if it's not real? And we'll kind of get to that shortly, okay? But, that's in the Earth reference frame. We have this free body diagram, right? So I'll keep going. I'll come back to that maybe. Again, in the Earth's reference frame is critical. Okay, and hopefully that'll become more obvious as I go through the rest of this. Do you feel like you're accelerating? Well, the answer actually is yes. In which way do you feel like you're accelerating if you're falling at terminal velocity? Well, in reality, you actually feel the same as if you're standing on the ground. You feel like you're accelerating up, right? But of course, your brain's going to trick you into thinking that you feel like you're, I guess I have their accelerating down, but it would actually feel like, the same as, feel the same, I don't know if it would or not, as standing on the ground. So there's a theory about cats to do with this. This is why I'm modifying that. So if you've probably heard of stories of cats falling off of very tall balconies and things like that and surviving. So the theory is that if the cat is accelerating towards the ground, it doesn't have that force underneath it that it's used to, and so it's nervous, right? So it's going to be very stressed and muscles all tensed and upset. Basically, hitting the ground like that is way more dangerous to a body because your muscles aren't flexible; they're all stiff, right? If a cat falls a far enough distance to end up in terminal velocity, then it basically starts to feel like it's standing on the ground. Now it has that force upwards on it that's balancing gravity, kind of like normal, right? Literally that normal force that we're used to. And so then the cat starts to just become comfortable, I guess, and feel like, oh, this feels kind of normal, and it relaxes and hits the ground with its muscles all relaxed and survives. It's the unfortunate drunk driver situation, right? You hear all the time of drunk drivers surviving, and the people that they collided with die, and because the people that are aware of what's going on are seeing this accident coming and are upset and muscles tense up, whereas the oblivious, irresponsible, terrible driver is completely unaware and relaxed when the accident happens. right? So there's a bit of an extra link there that I wasn't planning on talking about, but here we go. There it went, or whatever. All right, so now note, let's just keep this one paragraph at a time here. Even though gravity is not actually a real force, okay, it is really just the result of being in the curved area spacetime, right? It is still a very real effect when you are in the reference frame, in a reference frame near a large mass like Earth. So in an Earth reference frame, gravity is a very real effect, and it's a very real force to label on diagrams and so on. So this here, we can label that because in the reference frame that this is for, that gravity force is there. In order to keep you accelerating towards the Earth, there's a very real force, a normal force needed in the upward direction. That's obviously balancing that quote unquote force of gravity, which very much is real in the Earth reference frame. Okay, but I'm not saying that this other stuff is false. I'm not saying that gravity is a real force. I'm just saying that it's an effect that's really there in the Earth reference frame. So compare that to so just like we know, yeah, here we go. So just like you can refer to the Earth's reference frame as a non-inertial reference frame. And so to clarify what that means, we're saying that's equivalent to being inside of a rocket ship that's accelerating up at 9.8 meters per second squared. In such a rocket ship's reference frame, a normal force would also be needed to keep from accelerating down, in quotes, because it would just be opposite to the direction of the actual acceleration of the rocket ship. So the apparent force towards the floor inside the rocket ship clearly is not a real force, even though it has a very real effect in that reference frame and would have to be put on diagrams for analysis of motions within that rocket ship. So really, the Earth is kind of like a rocket ship, right? You feel like you're accelerating up all the time because of your existence in a curved space-time field, instead of actually being because you're accelerating up. Right? Einstein's genius was to realize that the two are indistinguishable, and it led to some pretty amazing consequences in general relativity, including time dilation and all sorts of crazy stuff. In fact, if Einstein didn't realize all that stuff, we would not have a properly functioning GPS network system. Because the clocks that are in the GPS satellites need to have all of the effects of general relativity programmed into them so that they keep time properly. So more about that later in grade 12. Right? So we're kind of set up to be able to talk, to talk about another non-inertial reference frame that I think we can handle here. Our circular motion is in grade 12, but I think we talk about this a bit. We should be able to picture how there's a force needed towards the center of a circle, right? So in order to travel in this circle, circular motion, there would be a force needed towards the center, and that's actually called the centripetal force. We'll see that in grade 12. If you didn't have that force on you, if there's a hole in the floor, you would just continue to go with your constant motion, right? So that's just basically your inertia, your inertial path or whatever. Let's call it that. Right, that would be your inertial path. So basically, you need a force towards the center to go in a circle. Picture something tied to a string whirling around. If the string breaks, the thing stops whirling around. It goes off on a straight tangential path. In the reference frame of the circular motion, that would be a non-inertial reference frame. So this is actually, I say it as NERF all the time in grade 12 because it's just long words, right? But non-inertial reference frame. Okay, so in the non-inertial reference frame, the force up is needed to balance the very real force in that reference frame of the outward force, and that's the one that we call the centrifugal. Okay, that centrifugal force clearly is not actually a real force, but in the reference frame, right, in that non-inertial reference frame, it is a real force in that frame. So I'm just putting this out there for now, just to help you be okay with the idea that gravity isn't actually a real force, but of course we need to actually work with it as if it's a real force in the Earth's reference frame. Okay, so this is a real force, but only in the non-inertial reference frame. if I should write this out at all so you know what NERF is here. Inertial reference frame. Rotating, I'm going to say actually. So this one's non-inertial because it's rotating, whereas the rocket ship was non-inertial because the rocket was accelerating, like blasting, applying a force upwards. Right. So these are artist depictions of what a spaceship could look like that would have artificial gravity. So the rotation, this rotation like this maybe, right, would make it so that a force is this way is needed to basically, I should do this one maybe in green. So that rotation makes this force very real in that reference frame, right? And so, in a very advanced version of this, you could have like, cities or parks and, rivers and so on. Like all this stuff would have to have a force upwards on it, just like a normal force, to stay where it is. So it would be very much like well, it'd be a lot like gravity. Not entirely, actually, though. I'll show you why. So this video, I was going to include it, but man, there's so many corrections needed. Plus, there's way too much Elon Musk worshipping in it. But it says things like, as you go away from Earth, there's no more like it just has so many corrections needed. I can't play it. You can watch it if you want and pick out the obvious flaws, which should be obvious after we go through these good videos. So let's go. Is there actually anti-gravity? Okay.
In fictional movies, we have all seen how spaceships have a button that activates or deactivates gravity. But is that possible? To date, it has not been possible.
That kind of artificial gravity? No. Like the magical one, like in Star Trek, where the spaceship is obviously just stationed, like not rotating, basically, and you just turn on the artificial gravity machine. That's not real.
It's possible to create anything close to artificial gravity. The closest thing we could find is proposals for spaceships with centrifugal cabins. Have you
centrifugal cabins? They said centrifugal, which, anyways.
Have you seen how clothes stay on the walls of a dryer when it starts to spin? In the same way, if we could make a cylindrical ship that keeps turning, all the things inside would stick to the wall, giving the impression that they are under the effects of gravity. So the only way to mimic gravity in future spaceflight is with a cylindrical craft that can use centrifugal force.
So that first one of a journey through this. So this is a nice little video that someone made with a bucket that's spinning round and round. So this is how it could work. So this person has, I'll just pause it here. So there's just a view from the person's head, basically, or where the camera is, I should say. And then it's whirling around and around enough that the apple appears in this rotating non-inertial reference frame to fall towards the bottom of the bucket over and over again. Okay. Clearly, you can tell by the background what's really going on, but in that reference frame, that force towards the center is necessary. The hands holding the apple, the force towards the center, is necessary to stop the apple from falling down. So there's artificial gravity in that. There's a very real effect in that non-inertial reference frame. Okay, so that's the centrifugal force in that non-inertial reference frame. So the free body diagram would be centrifugal force outward, applied force necessary towards the center of the circle to balance that force and have zero acceleration relative to the bucket. The bucket is your non-inertial reference frame. All right. Very nice little video there. So anti-gravity, artificial gravity. I remember I said it would be a lot like gravity, but not quite. Well, I'll show you this one because it's a good, really good analysis of how it would be good, but it would be weird.
Centrifuges are weird. They are great for providing artificial gravity in space, but you would experience some weird things living in one. Running against a rotation
not aliens tackling you. So
would make you feel lighter. Run fast enough and you become weightless. You basically cancel the rotation of the centrifuge.
So if you run against the motion, you're slowing your rotation down. So the effect of gravity would reduce. So you'd feel lighter if you run fast enough. And if you're able to run, like if it was a design that the rotation was slow enough, you could actually run fast enough. You'd be weightless inside of there. You wouldn't have a normal force, right? So again, the proper term better term would be normal forcelessness. You don't need a normal force. Of course, if there's air in there, you would slow down, right? Because of air resistance, so it wouldn't stay like that. But if this was, if you had a spacesuit on and there was no air in here, I guess you could get moving fast enough that you'd just be stationary, and the spaceship would be going around you, right? So you'd be stationary relative to like the overall craft, and the spaceship would just be rotating around you. You'd have the sensation of like flying like Superman through this long circular hallway.
With the rotation would have the opposite effect, making you feel heavier, and dropping something would
This is the one that's kind of surprising, right? Dropping something
be trippy. For you, the ball won't fall in a straight line, even though from an outsider perspective, it does. You can probably imagine what throwing something must look like. Super weird. Throw the ball hard enough against the rotation, and you could even hit the back of your own head. That's why you want your centrifuge to be as big as possible. The bigger you make it, the less noticeable those Coriolis effects will be. Centrifuges
so
are weird.
Fancy word there's Coriolis effect. You can look it up separately if you want. And what's the last one here? Can we create this guy is so in comparison to the wrong physics statements in this one, this guy clearly has it sorted out in his head as to the actual physics of things. So it's a really good one. And I should say too, like that's the problem with trying to learn this stuff is there's so many wrong videos out there. I kind of want to play the wrong one. Actually, I might actually, because I can point out the mistakes to help you, resist or like not have those stick in your brain better than the real ones.
One of the biggest problems we face when traveling in space is the atrophy our bodies endure while in microgravity. The astronauts on the International Space Station have to exercise several times a day to maintain their bone and muscle strength. But is there an alternative? Can we create artificial gravity? I'm sure you've seen the idea before in movies like 2001, A Space Odyssey, where the entire space station spins to create artificial gravity. People inside can now walk comfortably, just like they do on Earth. It does this by exploiting centrifugal force. Now it seems that whenever someone mentions centrifugal force, angry mobs will show up in the comment section declaring it isn't real, which just isn't the case. Let's see why.
So it's quite often that physics teachers will say that centrifugal force is not a real force because, like I showed you in the slide previously, it clearly isn't a real force. But the issue is that in that non-inertial reference frame, it has a very real effect, and it is therefore a very real force in that reference frame, right? It's just that it's not actually real on a grander scale. They don't word that well here, but
NASA developed this huge centrifuge to test the possibility of simulated gravity back in the 1960s. Here we're looking from an inertial frame of reference. That just means we're looking from an outside perspective, and we can clearly see that
it looks like it had like a rope, like the person was suspended vertically, and then found that they, very much had a real force on their feet towards the center to balance that perceived real force in that rotating reference frame.
There's no force pulling this guy outwards. It is just his inertia carrying him forward, and the floor he is walking on provides the centripetal force to prevent him from flying off.
Centripetal or centripetal, different pronunciations. So this little arm here is providing the force upwards against actual gravity, or due to Earth, I should say. And then the gravity to do the rotation he's experiencing. That's how he's able to walk like normal on the side of the. He feels a normal force from that wall pointing towards the center.
But what happens if our reference frame moves with the astronaut? This is called a rotating reference frame, or a non-inertial reference frame. To him, the rest of the world is moving, and he is standing stationary. In this reference frame, centrifugal force is absolutely a real and measurable force, pushing him downwards
in this reference frame. It's absolutely a real measurable effect, right?
It's like gravity. The only thing that is fictitious is his perception of what is causing it. This occurs because in physics and engineering, we must balance forces. The system has to be in equilibrium.
You'll see how he looks kind of lighter because he's reducing his velocity, or increasing his velocity against the velocity that's actually going on. It's so confusing to talk about.
Newton's third law states for every action there's an equal and opposite reaction. So if centripetal force exists in this reference frame, there has to be a force pushing him outwards. That is centrifugal force, and the moment the rotation stops, it vanishes again. So if this works so well...
So they stopped the rotation, and then he's like no longer walking on the floor. He's just hanging from a rope, right?
Well, why haven't we seen a spinning space station yet? Well, one problem is size. To make this practical, we need a massive ship, which would be incredibly expensive to get into orbit. The acceleration your body will experience is directly proportional to the speed and radius of the space station. We can calculate the gravity Space Station V from 2001, The Space Odyssey, would generate. It's some pretty simple math. The Space Station V had a diameter of 300 meters and spun on its axis once every 60 seconds. That would put its gravity at about the same as the Moon's. For it to have a gravity similar to Earth's, it would need to spin once every 24 seconds.
The calculations behind the scenes of this can be done in grade 12, but it's not something we do in this course. I'm just giving you the idea of it, so that when later on we run numbers to do with it, you're not worried about the concept as much, hopefully, at that point, because it'll have been in your brain for a while and festered around in there for a while and started to feel more comfortable.
If we were to make this a realistic size, let's say the same as the International Space Station, it would need to spin once every 10 seconds. This would probably be pretty disorientating. Just ask Sandra Bullock. Another problem we face on smaller stations like this is the gradient in acceleration you would experience. Because the acceleration is directly proportional to the distance to the rotational center, your head will experience less artificial gravity than your feet. This would force the blood to your feet, just like when you spin a bucket of water around. This effect diminishes with larger stations, so to make a practical space station with artificial gravity, the station would have to be huge, which is simply too expensive. Besides, the ISS is most valuable to us as a laboratory to test the effects of microgravity. But what if money was not an issue? What would it take to get a space station like...
So they're saying there's maybe not a lot of incentive to make this International Space Station be like this, because a lot of the tests, they go up there on purpose to be able to test the effects of so-called artificial or weightlessness, right? Or normal forcelessness. But my argument would be, well, maybe we should aim for having artificial gravity all the time, since that's going to be healthier. Like, why do we care what the effects of artificial gravity would be? Like, shouldn't we just have, what the effects of normal forcelessness or weightlessness would be? Instead, I think we should just go for this, but you'll see it's pretty tough to do.
Elysium, built for the mega-rich as an escape from the turmoil on Earth into orbit. Elysium dwarfs Space Station V, measuring in at 60 kilometers wide, and it is estimated to weigh about 1 million metric tons.
Holy, that's the one they were showing before, little dot, right? There's the one that would be sort of, more functional.
SpaceX can currently launch 1 kilogram into space for about $2,700 with their Falcon 9 rocket. This will be reduced to $1,650 per kilo when they launch their Falcon 9 Heavy variant at the end of the year. But it would take over 18,000 launches to bring the 1 million metric tons to low Earth orbit. That's $1.65 trillion to just get the materials of Elysium into space with current technologies. Then we have to worry about the cost of materials and engineering that would go into building something of this magnitude. That is far more difficult to calculate, but we can take some clues from the ISS. It is estimated to have cost about $150 billion in total. It took 36 shuttle flights at a cost of $1.4 billion each to bring the materials into space. That's a total cost of $50.4 billion. So the launch costs were just 33% of the total cost. A conservative estimate for the cost of Elysium could put it at $5 trillion. That's 62.3 Bill Gates. But there are 500,000 people on board Elysium. So if the costs were split between everyone, that would be about 10 million each. That isn't so far-fetched, and the price of space travel is destined to reduce in future.
Not so far-fetched in terms of our oligarchs we have in our world that are harboring all of our wealth, right? There's lots of people that have 10 million to throw around, but
we do have materials strong enough to build a structure like this. The forces on Elysium would be similar to the ISS, other than the additional stress created by centripetal and centrifugal force. It's interesting to note that the designers of Elysium took note of this. The stress in spinning structures like this would decrease as you move away from the rotational center. This means it would need a stronger structure the closer you get to the center. This clearly influenced their design with these tapering spokes. But we run into some problems when we realize there isn't enough aluminium in the world to build this thing. It would take at least 10 years worth of the world's total aluminium production just to build the structure. This would cause a huge surge in the cost of material. An alternative method could be sourcing the materials from space. This could reduce the launch costs, and there's plenty of metallic material available on the moon and near-Earth asteroids. So this technology is definitely possible. Our only barriers are launch costs and material availability. Something on the scale of Space Station V would be easily achievable. Who knows, maybe we'll be traveling to space as tourists in the near future. Once again, thanks for watching.
So, yeah, that is hopefully understandable. So the end result, though, we'll obviously keep working with the very real gravity force in that Earth reference frame that we're talking about, right, in our physics work. All right. So, yeah, hopefully that makes some sense. And thanks for watching.